There we go. All right, so today is probably the last day we're going to talk about carburetors. We'll finish it off today. And I kind of thought I would try something cool and see if I can do it, which is what I sort of tried yesterday, but failed. So you guys should be looking at an instrument panel, correct?
Yeah.
Yep.
Okay, this is X-Flight. So I have not tried this before, but I'm going to give it a shot now. So this is actually out of a Beach Baron. And so what I have is the pretty much the whole cockpit. We're on the ground, and I can remove the yokes. I'm not a X-plane expert. I actually bought it mostly for what we're going to do right now so that I could share with you guys some stuff. So we take a look at what's going on. And what I want to do is pretty much just take you guys in a cockpit and do a run up. So we'll look at the gauges, because when I zoom out, I want you to know what the gauges are. I'll move my microphone.
Pressure.
There we go. Okay, so we have our manifold. Now this is a twin engine, and I selected this one for that reason, because it is a twin and it does have constant speed propellers on it, so we could run one and not run one. And although this isn't extremely accurate, it's pretty close. I also have the Microsoft Flight Sim, and so I got the trial of this one, and this one actually represents, or from a mechanic standpoint, I thought it was more accurate. So, all right, there's our tack gauges. Can you see the arrow floating around?
Yeah.
Okay, good.
Yeah.
So this right here is a synchronizer indicator, and it will actually rotate towards the faster engine so that you know if your engines are in sync or not. So you'll know what that is when it's moving this way, then the right engine's faster. If it's this way, the left engine's faster. And if it looks like that, they're both operating at the same speed. And right now they are very much operating at the same speed, which is standing still. So, all right, we have our fuel flow. We're going to learn here in a couple weeks that these fuel flow gauges are not really fuel flow gauges. They are pressure gauges that are calibrated to read fuel flow. That'll mean more to you later, but it doesn't matter now. Just get used to that stuff. All right, unfortunately, Beechcraft here is giving me my temps in Celsius. 20, so on the right we have EGT, which is 20 degrees per division, which is about 68 degrees Fahrenheit, and our CHT on the left. So CHT, cylinder head, EGT, exhaust gas, oil temp, oil pressure, and oops, we'll go down here. So down here I have all of my controls. So we have throttle, left, right, propellers, left, right, and mixture, left, right.
Uh-huh.
All right, so this gauge right here, let me see what else we're gonna look at. I don't think there's anything on this side we're actually gonna be looking at, because this is all flight instruments, but we can start with this one right here, which is my altimeter. And if I wanted to know, well, as I explained before, the altimeter should match the manifold pressure, right? And so does my manifold pressure match my altimeter?
Yes.
Kind of. If you look right here, it's maybe a little fuzzy just to me. It says 29.84 inches. So this should say that if this is calibrated right. Well, it just so happens that in this program, it asked me where I want to start, and I said McClellan. And so McClellan's altitude is 74 feet. So I'm moving this right here. So if oops, too far. If I bring this to about 74 feet, 2, 4, 6, 8, back up a little bit. Maybe one click. That's about right. Now look right here. My barometric pressure is 29.92.
Standard day.
So hopefully you follow that. If I set this needle to my actual altitude, which is 74 feet, according to where this aircraft is setting in the program, then this tells me my barometric pressure. And barometric pressure just happens to be a standard day. All right. So I'll look over here, and that says pretty much 29.92 in that one. So they're matched, so they're good. So that's what we're gonna do. So, all right, let me come back over here, start this thing up. Nice thing about this program is the engines actually start real easy. So I thought.
Got a dead battery.
Okay, I give up. Why would it not start? It's a stupid
You figured
program.
out we got
Is the key in?
It doesn't have a key.
Oh,
Are you kidding me?
Fuel is on and everything else.
Fuel pumps. I didn't think I had to mess with any of that stuff.
Sure.
So is this X plane is what it's called, or X flight?
explain.
Explain.
X
Is that 11, Kevin?
Yeah.
Okay,
That's so
my son
dope.
has the same one.
Well, that just sucked. How embarrassing is that?
Good troubleshooting demo.
I know, good troubleshooting demo. Well, I don't really know the program. I know how to run an actual plane. So I'm
Check your
looking.
circuit breakers.
Circuit breakers are in. I need my fuel pump.
To your fuel boost pump. But I don't
Boost
know.
pump, they're up.
No fuel.
They're on.
Did you move the fuel selector switch?
What's that?
The fuel selector switch.
I didn't mess with it.
Oh,
I can't touch anything else at the same time.
Up.
What?
There's a thing that says on and up on the bottom.
All right.
Take it to Best Buy.
Huh?
Take it to Best Buy.
Take it to buy now. Hang on. Let me just restart it. I had this running a long time ago, so I don't really know what the. I think it's simulating I flooded it. Oh, funny. All right, let's see. Oh, unpaused. Yeah, that's what it is. The fuel pumps have been running for like 4 hours. So I think it ran it out of fuel because I did this like earlier today. So let me-
Can you restart the
yeah.
That's so great. Realism at its
I know.
finest. In real life, would that happen? Where would all the gas go? To just
I'll be all over the floor right now. Well, let me do something here. Let me,
There was a
No,
thing
no.
that said start engines under flight.
yeah. Where?
Second
There.
from right there.
Thanks.
There you go.
They don't sound very good. Oh, see, they're both on start right now. They're actually not starting. See, they are not starting. So I need to go main menu.
I guess save flight and open a new flight?
I want to, sure. Yeah, I don't want to do that.
Where?
The heck? Best laid plans all fall apart.
You want to quit
Starting the
explain?
flight.
Keith, explain and yeah.
There we
That's
go.
gonna take a while.
Yeah. Oh, we can talk about something else here. Which is funny because I've heard this weird noise out of my computer for the last several hours. I did not realize that it was the fuel pumps on that thing running.
It burned up or burned out or something.
Yeah, just a second. We'll just edit this part out, right?
Yep.
That's funny. As class was starting, I was landing a plane in that game on my phone.
No, really?
don't worry, we'll fix it in post.
Let's see. J-Rod, does this mean I'd be able to fly an airplane after this? Absolutely. Just don't tell him. Just don't tell him I said so. So, all right, well, that reloads. We'll get to it. And we can get back to some regular work. Because yes, that will take a while to load scenery. It's a big program. Okay, some notes. And we'll get back to that. All right, so I'm down to number 7. There we go. Oh, it started.
Wind calm, visibility more than 10. Sky clear, temperature 15, dew point -14. Altimeter 2992.
All right, let's turn off the comms. Zoom in. Get rid of the yokes. All right, you guys seeing this now?
Yeah.
Okay.
Yep.
Yep.
Yes.
Okay, so we've gone through all this. Now you can see this right here. You can, because we're in idle and I don't have the prop sync on. Prop sync right here. If I turn the prop sync on, once the governors are actually engaged, then it should be able to allow. But really, technically, the governors don't engage quite yet. So hopefully I have the brakes set. And so let's bring up the left engine. Well, actually, I want to shut down is what I really want. This time we'll turn off the boost pumps. All right. And with the boost pumps, I should have my fuel flow is at 0. And if I turn the boost pump on, see how the fuel flow comes up? That's why I wouldn't start, because I literally just dumped all the fuel out of the plane and the simulation actually realized that. So, because I just shut it off and walked away. So, okay. So here we are on the ground with the engines off, and we verified that we have our manifold pressure is in fact showing atmospheric pressure. So I'll leave the right engine off for now. So, okay, so now we're running the left engine. And so take a look at the manifold pressure. I was saying, so we are really, really low. Remember that? And the reason why it's really low as opposed to the right engine, which is off, is that I have the throttle valve closed and the engine, which is an air pump, is sucking against that and starving for air, so to speak. So it's really trying to pull in some air. So I have a significant vacuum, a big time vacuum. And the other thing I can tell about this particular program is this is not a turbocharged engine because it doesn't go above 30 inches. If it was turbocharged, it would be possibly coming up in green arc more than manifold. So we can see our fuel flow in gallons per hour. And let me see. Temperatures are actually going to start really coming up on this, but you can see my EGT is up right away because it's just exhaust gas. And oil temp, just going to be fun to note where this stuff goes. So, all right. Get a full view here. Oops. There we go. All right, so let's bring the power up. Now, as I bring the power up, note the relationship between the RPM and the manifold. So whenever it's very sensitive. So as the RPM comes up, the manifold pressure is going to come up. Remember yesterday I talked about this split where it wasn't. Remember, that was because I was adjusting the RPM with the idle mixtures. That's totally different. So under normal circumstances, this is what I'm going to see. And under normal circumstances, I would never abuse an aircraft like I'm doing to this thing right now. Because if you start watching, the temperatures are already climbing up over here, redlining there. This one's going to get way up here. But let me see if I can zoom in just a little bit and still have control. Let's watch our EGT. So EGT, sorry, got too many. And I'm going to pull back the mixture control. And as I pull it back, EGT should start coming up a little bit. And also my RPM will come up a little bit. So their RPM's now at red line, and the governor will actually prevent it from going any further. But watch my EGT, how that thing's coming up. So it peaked out right about Where did it peak? So if I try and find the peak, so it's peaking out about right there. Pull back just a little bit more. Going the wrong way. And so once I find peak, all right, so now I'm at peak EGT, right? So if I pull it back a little bit, I'm going to go lean of peak. And if I go forward, I'm going to go rich of peak. So we'll go lean of peak about 100 degrees. Actually, it's still climbing up.
Yeah, your oil temp is no good.
Oh, there's peak. All right, so there's peak. That right there's 70 degrees thereabouts, lean of peak. And you can see when I did that, my fuel flow gauge came way down. So right now I'm running at what, about 12 and a half gallons per hour. We can take a look and see where my RPM is. RPM's at 2550. Manifold pressure at 26. But right now, keep in mind, I'm running this like it's a fixed pitch prop. All right, or I can go rich of peak to the same spot, bring it up. Going rich, rich, rich. Okay, same spot. Oh, little overshot a little bit. So now I'm on the rich of peak side. And look at my fuel flow is way down here. It was way up here before. So it's way down here. Same EGT pretty much. Look at my oil temp. That's not good. CHT temp. That's not good. So that's what that looks like. Let me, oops. Pressing too many buttons at once. Okay. I don't know. Even though it's a simulator, I think I felt sorry for that left engine. I got to let off of it. All right. What we're going to have to get used to is we haven't messed with these blue knobs yet. So what I was doing, the aircraft really acts a lot like just a fixed pitch propeller, where the black knob controls both the RPM and you can see the manifold pressure move. That's always going to happen. So, but the black knob is directly controlling RPM the way I have it set up. With these two blue handles forward, this just controls RPM. So I go forward, I get RPM, pull it back, RPM goes down. All right, but once I start messing with all right, there we go. In a constant speed aircraft with a constant speed propeller, you actually have them designed so they go all the way up to red line on the ground. That's not what you do with a fixed pitch. That's very different. So with a constant speed propeller, it's going to go to red line, and what's keeping it going any further than red line is the propeller actually starts to limit the RPM of the engine. And then once I bring my throttles all the way up or reasonably high, I now start controlling the RPM with the propellers. So as I pull this back, watch the propeller is now controlling the RPM, and look at the manifold pressure. It more or less stays the same for quite a while because the black knob now controls manifold pressure. So I've got it set at about 2100 RPM. Now, if I pull this back, the RPM stays the same and the manifold pressure starts moving. So I'm actually decreasing power because the manifold's going down. Now it'll get to a point where the prop can't handle that anymore and it just starts to decrease RPM. But for the most part, once you're up in the operating range, the throttles literally control manifold pressure, nothing else, and the props control RPM. Oh, and that's the job of what it's supposed to do. So anyway, questions on that one?
No.
All right, so let's see what happens if, when I pull this knob back to shut down the engine, what should happen to my RPM?
Go down. Oh, it should.
Could go up 25 to 50 and then go down.
Yeah.
I don't know if the program will do it. So watch the left RPM real close.
Yeah.
Did it go up?
It did. It did go up a little bit.
Nice. All right, then it shuts down. Well, if I could get it to stay. There we go. Shut down, shut down. Can I switch planes? Yes.
Rio Linda weather. Wind calm. Visibility more than 10. Sky clear.
All right, so this particular plane, this is a single engine Cessna 172, where it's actually got a fixed pitch propeller on it. So the thing you're gonna notice about, can you guys hear the prop noise and everything?
Not really.
A little
Kind of.
bit, all right, I just make sure it's not
Yeah,
distracting.
No.
I can't hear it.
It's kind of loud for me. I don't even know how to turn it down at this point. Probably have to spend all day to figure that out. I don't want the ATC window. Okay, so this does not have a manifold pressure. Why? Because you just don't need to look at that when you're flying a single. When you're flying or I shouldn't say it, when you're flying a fixed pitch prop. If you're flying an aircraft with a constant speed prop, you're actually going to set the prop and the throttle based upon your RPM and manifold pressure configurations. But in a plane like this, all you have is throttle. So if we look down here, all you got is a black knob and a red knob. So black knob makes the RPM go up. And now notice this one does not go to red line. That is called the static RPM. And I don't remember if we talked about that in the engine class, but the type certificate data sheet actually tells us what the static RPM of an aircraft is. And static RPM is the RPM without the aircraft moving, in the chocks, standing still. And it must be within a certain window. So if I did this in an actual airplane, which I did every annual, if the type certificate data sheet says, oh, well, it should be, what's that, 22 to 2300, I'm good, right?
Yeah.
I got 22 to 2300. Now, maybe the type certificate data sheet would say, not less than 2300 and not more than 2500. Well, it'd be bad because right now it's less than 2300. And the whole purpose behind that is that it's telling me how much power I'm producing. And you can do that with a fixed pitch propeller. You can't do it at the constant speed because the prop will just change pitch. The reason behind that is the propeller has to have an exact pitch based upon the type certificate data sheet. And with that pitch, if the engine is not producing enough power, then the RPM will be low. And if you have if you have the wrong prop on, if you have the wrong prop with too much pitch, you're gonna have low RPM. If you have the wrong prop with too little pitch, you're gonna have high RPM. So type certificate data sheet is gonna give you that number right there and tell you exactly where you need to be. So we're looking good there. So this one, we have EGT over here, and we can pretty much do the same thing. And pull this out until we get peak. This one's more sensitive. So, right, if I'm at peak and I push it in a little bit, is that rich at peak or lean at peak?
It's rich.
There you go. It should be rich at peak. If I pull it out, it's lean at peak. All right, so that's pretty much running up an airplane. Let's see. So if I pull, same thing, if I pull the mixture back, what position is it when I pull it all the way back?
Full
Oh,
lean.
lean.
That's idle cutout. That's idle cutout. So, but if I watch my EGT gauge, or, sorry, not EGT, I should be watching my TAC. Do I get a rise? Look at that. This one's easier to see. And now it quits. It's all right. So we're at 650.
So throttle all the way back is idle.
Yeah, throttle all the way back is idle. So I've got it in idle. Now, if I had it up here and I pull this back, normally you don't see any sort of rise at all. Now you do here, which just tells me it's running a little rich. But we check idle mixture with it all the way back. Oh. I can't make it not do that. Stop. There you go. Okay. All right. That's that. Hopefully that's fun.
You left the mixture in.
I think it'll be okay. All right. So just a couple little things to finish up here tonight. Let's see. Carburetor, carb. Disadvantages. Oops. Learn to spell letters. D-I-S. Oops. A-D-V-A-N-T-A-G-E. Disadvantages. Well, that doesn't even look like I wrote disadvantages. How about I try that one more time? Add. A-N-T-A-G-E. Look at that. Hey, that's actually a word now. All right. So some disadvantages to carburetors. Janet, did I land the plane? I never took off, Janet. I don't trust planes. All right. Number one, they don't work upside down.
That was going to be my first guess.
Well, you would have been right. Actually, they will work upside down as long as you keep positive G. And that's kind of hard to do. But as soon as you get a negative G, they don't work. They don't work right side up in negative G either. So they have a reasonably slow throttle response.
Hence the accelerator pump.
If it has it, not all of them have it. Some have accelerator wells. And so, yes, the accelerator pump does help that a lot. Probably the biggest disadvantage is they form ice rather easily.
Is it 7 or 8?
What do you want it to be? I can make it 7 or 8. I don't care. I just pulled out a page. Probably 8. All right. So they form ice easily. And you guys will get more of this in ice and rain, I think, in second year. Ice can form on the Venturi, even in hot weather. Unfortunately, both of those simulators, those aircraft have fuel injection systems. So that's different. So I couldn't run a carb heat. So remember, as fuel vaporizes, the temperature drops. Going back to day one stuff, we're talking about the whenever for fuel to vaporize, it has to absorb heat, which makes the stuff around it cold. When the temp drops below 32, when the temp drops below 32 degrees, that's inside the carburetor, 32F inside the carburetor, moisture in the air can freeze. Moisture in the air can freeze onto the Venturi and throttle plate. Now, if I am flying along at a cruise RPM, 70, 60, 75% RPM, and I start to get throttle ice in a fixed pitch prop, I'm going to start seeing a loss of RPM, and the engine will start running rougher. And at that point, I would turn on the carburetor heat to get rid of any ice that would build up. If I'm flying in an aircraft with a constant speed propeller, the propeller is going to do, the governor and the propeller will do their job and keep the RPM the same, but I will start losing manifold pressure because it starts making, takes the venturi, makes the venturi smaller and smaller. It's like the throttle plate's closing, restricting air, so the manifold pressure is going to go down and start running rough. And at that point, I would add carb heat. Now, one of the dangers here is when you go to land and you pull the power all the way back, if you get ice, it can actually freeze the throttle plate in position where all you have is idle, or it'll shut down, and you don't have a lot of heat at that point because the engine is now slowed way down, you're descending, so you have a loss of heat, which is, I believe, the reason why during landing, it's procedure that we always turn on the carburetor heat. Even if it's 110 degrees out, I'll pull carb heat on. It's just the procedure, it's what I do.
Where does carb heat come from?
Carb heat comes, carburetor heat as well as cabin heat come from the exhaust system. So we have our cylinders. Well, I guess we're gonna use red today. Have our cylinders, and the exhaust comes out of the cylinders, and it's gonna go into a muffler. All right, so that actually goes inside of the muffler, and then the muffler, make it go like this. Muffler goes out like that. All right, so the bad, nasty exhaust gases come in here, fill this up, and go down here, right? Okay, around this, all the way around it, so use blue, is a thin metal cover, if you will, that goes all the way around this. And this has a spot where we'll say fresh air. Fresh air comes in this way, and hot air goes out that way. So the fresh air comes in, goes around all of this, and out. And so the black and the blue, so to speak, they never touch. But if you somehow get a hole, if you get a little hole right here, or a crack or something like that, then all of this exhaust gas leaks out, and the exhaust gas intermingles, and the exhaust gas goes that way. And that's either, this hot air is either going to the carburetor on one side or the cabin on the other. So if it goes to this way to the carburetor, then you're just going to have a loss of power. If it goes this way to the cabin, you have a loss of life.
Carbon monoxide poisoning.
That is a fact.
Mm-hmm.
Let me see.
Hypoxia. I thought that only happens on jets.
No, hypoxia is
Hypoxia is different.
different. Yeah.
It's actually carbon monoxide poisoning, which blocks the oxygen to the red blood
In
cells.
your bloodstream. Yeah, in your bloodstream. Doesn't allow them to take in oxygen. Because then that's why you can tell you're kind of getting carbon monoxide poisoning, like if you're starting to feel dizzy or woozy. But a lot of the times you can't even really tell because the red blood cells are going up to your brain. So that's why typically you just pass out. You just start feeling sleepy and then pass out. There is no real like determination of, oh, I'm getting carbon monoxide poisoning. That's why people can go to bed, they have a carbon monoxide leak in their house and just die the next morning.
It's a lot like my lectures. It's odorless, colorless. You just kind of feel sleepy, and then before you know it, you go to sleep and you're dead. I was pulling up a picture for you here.
I know like a lot of aircraft have like electronic carbon monoxide system detectors, but like in a lot of small aircraft, like I have this little sticker that I change out every 3 months. If it turns brown in flight, then I know there's carbon monoxide in my.
Okay, so this right here it's just different styles of exhaust systems, but pretty much what I drew is this thing right down here. So that's that thin outer metal. This is what's behind that metal. So if we take off this, it's called a shroud, take it off, you're going to see this. So all of this area with these little pins sticking out, this is the fresh, non-poisonous air. and then the poisonous gas goes in that tube and out this tube. This is how Lycoming does their carburetor heat. It's really kind of funky, but it does work. So all they do is they just wrap this little piece of metal around the hot exhaust pipe right here. And so the air for the carburetor, when you turn on carb heat, is just going to go around this, down that little hole in the carburetor.
Are those little pins hollow on the carburetor?
I don't think so. I don't think they're hollow. That would be too risky. So, all right. Let's get rid of this. Thank you. Go back to this. All right. So we have carb heat. Let's see.
Kind of a question for you, Kevin. On a lot of like the newer aircraft, they have carbon monoxide leak detectors. Are those in the cabin, or are those on the actual, like near the muffler itself to the beginning of the leak?
No, the carbon monoxide detectors, as far as I know, they're all located in the cabin, not outside, because there's too much air flowing around, and it would be diluted air and wouldn't pick it up if it was near the engine. Yeah, thanks, Heath. Pins are just more surface area to pull the heat. Not all of them have pins. In fact, most of the airplanes I've worked on, they don't have those pins, but that one did. All right. So can freeze. This freezing can happen with outside air temps. That's also called OAT. Outside air temp. That's an official acronym. It can happen with outside air temps between 32 to 100 degrees. And the reason why you're not going to get ice below 32 degrees outside air temp is because the air is already frozen. So any ice crystals are already frozen. And it's shocking, but yes, if the high humidity and the right conditions, even if it's outside air of 100 degrees, you could get ice in the carburetor. So keep in mind that as ice forms, mixture becomes richer because you're blocking air. And because you're blocking the air, it starts to get richer in there. And let's see, eventually the ice can actually shut down the engine. So ice can shut down the engine. That's a bad thing. If you're flying around and you wait that long to let the ice actually kill the engine, chances are you're not going to get it restarted, because you need air flowing through to melt the ice. And at the point the engine shuts down, then the exhaust starts cooling off, and it all kind of goes pretty bad at that point. So let's see, ice prevention. Ice prevention / removal. When we talk about, I guess I'll talk about that in a minute. So ice prevention removal. Well, we'll say that there, as far as this goes, there are two types of ice that we need to be concerned with. Impact and throttle. Impact and throttle. Impact ice is ice, just like it sounds. It came from somewhere and hit. So if you're flying around in freezing conditions, you have impact ice that will hit the aircraft. And that impact ice can actually will impact and strike against the air filter and then start to plug up the air filter. That's a really bad thing, because carb heat will do nothing for you, because the heat is on the other side of the filter. So it just plugs up the filter, and that's bad. The good news is, even though you can't remove that ice, when you open up the carburetor heat, the air source comes from someplace else. So you always have an alternate source of air coming in. In fact, aircraft that don't even need carburetor heat, something with fuel injection, they even have their own alternate air source. A lot of times it's just a door that's spring loaded on a magnet. And if the suction gets too great because the filter's been plugged up, then the suction gets built up, the aircraft, the engine's trying to suck a bunch of air. It can't, so it sucks this door open and boom, get a bunch of heat. Now and the alternate air door is always inside of the nacelle area where the engine is, where the air is already pretty hot. The bad part is, you got good air, but the alternate air, carb heat, all of those things are in fact unfiltered air. So you'll see me when I fly my airplane, I've taken some of you guys with, carb heat goes on, I land the plane. First thing I do when I hit the ground is carb heat off because it's completely unfiltered air down there on the ground, and I don't like that. All unfiltered. And I think that's a safety reason. You don't want two filters. If you're going to get one plugged, it's like, well, why risk it? So, yeah, carb heat is unfiltered. Yes. Cool? No, it's hot. All right. In the world of icing and planes, there are two different ways of looking at it. There is de-ice, and then there is anti-ice. Let me see. I'm trying to, well, I'll write it down later. Otherwise, I got to scroll too far. And you guys are freak on me. All right. So de-ice equals removed formed ice. That's when you removed formed ice, as opposed to anti-ice, where you actually prevent ice. So under most circumstances, it's either one or the other. But carb heat is actually one of the few things that I can think of that is both a de-ice, where it will remove the ice, and an anti-ice, where you can actually put it on just to keep ice from forming. I got too many notes here for this. So let me see. I'm going to try and condense it here, finish this off. So let's see. Well, let's go with it. So de-ice. So how do we de-ice? Well, we add carburetor heat, add carb heat. And it's just a lever, square lever or triangular, either. Depends on how it's rotated in your aircraft. That's the proper way, is a little diamond. So little diamond, just carb heat, black, pull it on, push off. Pull on, push off. So add carb heat. So here's the thing. So you're flying along, and we'll say we're flying in a 172 or 150 that has a fixed pitch prop. And we start to feel a little vibration. The engine's not quite running the way it was a little bit ago, and a little rough. And you look over and, hey, I noticed that my RPM is a little bit less than it was a little bit ago. So I kind of think about it, and yeah, I'm at a kind of a high power setting, cruise, and that's kind of an unusual carb spot, a carb ice spot, but it's a really cold day, it's possible. So I think, well, I'm going to try it. So I reach over and I pull my carb heat on, and the very first thing that's going to happen is, no matter what, it's going to get worse. If you have ice, it's going to get worse. If you don't have ice, it's going to get worse. And the reason why is because, we'll say if we don't have ice and I pull carb heat on, the air is now very hot, and that hot air is less dense, and you just made the carburetor a whole bunch richer. And so it's not going to run very well. Well, I shouldn't say that. It won't run as well, especially if you have it leaned out properly. So you'll notice a change, not much. All right, but now let's say I did have carb heat. So aircraft is already running kind of terrible, and I pull on the carb heat, and now same thing, same rule applies. I've added heat, I've enriched the mixture, and it was running bad before. It's going to run even worse now because I added the heat. Which is decrease in density, which is already a decrease in horsepower. I've enriched the mixture when I pulled that out. And now, as ice starts to melt, I'm going to be ingesting water and ice into the engine, and that's going to get even worse. And so things are going to get a lot better before they get worse. And so as that ice runs through the engine, and maybe it's going to interrupt the fuel flow around the nozzle coming out. And then as the ice disappears, the engine will get a little bit better, and then I'll push the carb heat off, and now everything's going to get a whole bunch better. Like, wait, there it was much better. So, so add carb heat, engine. I'll just write it as that. Engine will be running rough from ice. Will already be running rough from ice, from the ice. So the addition of hot air Hot air will enrich in the mixture. Will enrich the air. Well, sorry, I did not enrich the air. Enrich the mixture because the air got hot. The addition of hot air will enrich the mixture. Will enrich the mixture more. Makes it richer now, which equals runs even worse. All right, so we got an engine that's running rough from ice, add some hot air, mixture becomes rich, and now it runs a little bit worse. Some notes on that. So carb heat adds about 100 degrees Fahrenheit to the air temp, to inlet air. Inlet air, that's what I'll say, inlet air. And that is about a 10% reduction in power. That's a lot of reduction, actually. That'd be 10 horsepower in my engine. So C, as ice breaks off, engine runs even worse. And now we're going to have somewhat of a pucker factor on that one. When ice is removed, engine will run stable. Some power will return, and then when carb heat is off, engine will return to normal. Engine will return to normal power. There we go. All right, it is in fact break time. Yes, I was watching the clock. So I will leave this there and see you guys in 10 minutes.